Hello, everyone. Today I will introduce a new IoTDB, Apache Incubating project to you called IoTDB, and it's an Internet of Things database. Does anyone hear about IoTDB? Hands up. Okay, good. There are 2 persons. That's why I stand here, because I want to introduce it to all of you. Okay, let's see who we are. When we say IoTDB, IoTDB is IoT plus DB. It's a database for managing IoT data, especially for industrial IoT data. Here, the IoT data means the time series data. And when I introduced the IoTDB to others, many people asked me, is IoTDB, is there a blank space between the word IoT and the DB? I said no, IoTDB is a software product, while IoTDB means a kind of database. So if you want to search something about IoTDB, you can use them as one word. Do not use blank space. And IoTDB is very young, and I'm very glad to introduce IoTDB in Germany because, as you know, Germany is a famous country for industrial. And when I came this country, I found many substances about IoTDB in Berlin. Why to say that? These photos are taken around the building, and we can see the wind turbines, the excavators, the trunks, and modern vehicle factories, and all of these may belong to industrial IoT scenarios. And what is more important, I found many DB logos in Berlin, especially at the metro stations. Actually, it has different meaning with database. It seems it's a Germany train, short for German train. But anyway, we got IoT and DB in Germany now, even though this is a code joke. And then let's turn back and introduce what a real IoTDB is. IoTDB is proposed from Tsinghua University in China and is donated to Apache community at 18 November 2018. Initially, only some staff and students in Tsinghua University devoted for it, but now there are some companies and university students devoting for it. For example, like Pragmatic Minds, Germany company. And you can see Lenovo and Microsoft and some other companies are coding for it and use them in some applications. As for me, I was a PhD student in Tsinghua University and then a PhD postdoc in Tsinghua University again. And now I'm an assistant researcher in Tsinghua University once again. Though I have no experience that working in some industrial companies, but I really worked for managing time series data for several years. From 2012, I began to use Apache Cassandra to managing time series data in some companies in China to store the time series data. And we found some performance problems. For example, the replic consistency problem. For example, when you scale out the cluster, you have to wait a long time to migrate data from one node, old node to new node. And if your memory is not enough, you will get a lot of small files, and you will get an exception called too many open files and something wrong. So we began to develop IoTDB, and before developing IoTDB, my favorite Apache project is Cassandra, but now it's absolutely IoTDB. And then let's introduce Julian.
Yeah. So hi everybody, my name is Julian. I am one of the founders of a small startup called Pragmatic Minds. We have a spin-off, Pragmatic Industries, where we do a lot of industry applications. So we hit a lot of the issues that IoTDB is solving. So when I heard first about IoTDB, I was really excited. I was one of the first ones to join the mailing list, and I had the luck that I was the first committer who's not the initial committer, and we really playing around a lot with IoTDB as it solves many problems we have. As you see with the other projects I'm involved, we are really all around this industrial IoT space. So not only IoT as, I don't know, smart thermostats, but like real big machines. And yeah, this is basically, I want to tell you a bit about the exact use case or the situations where you run into issues with the setup you currently have. A major driving force is what we in Germany call Industry 4.0. As you may know, Germany is very well known for its machine manufacturers, in its big industrial machines. And it's a pretty big thing here in China. It's called the Industry Internet, in the US also. So people really start to think about, not only about building the machines, but of using the data these machines are producing. And this is something which, yeah, since 3 or 4 years really goes off. And people are really interested in those data sets, and they are huge because those machines have tons of sensors. Oh, let's go a bit more. Oh, sorry. Go a bit further. So these are really examples of machines where people want, for different reasons, want to investigate the data. And you have data in different levels, but down to millisecond frequencies, where you're interested in vibrations to see if a motor will soon break, but also only in a second range or on a or on some minutes. But overall, such a machine has hundreds to thousands of sensors on it. So it's really a lot of data coming together. There are other domains where also tons of data is collected, like meteorology is very well known for collecting tons of data, and also other data sets play a role, but we are mostly interested in, I would say, those two domains where there's really tons of data generated currently. Currently, a typical setup basically is you have the machines generating the data, then you have some kind of messaging system, and then you insert it in some kind of server, and later on transfer to an RDBMS where you make it available for OLAP applications, basically. And the current setup could be something like this. We're here at Apache Council. We show a lot of Apache projects which could be integrated in the process. Sometimes PLC4X is like the source, but also other projects play a role. We just heard about NiFi or MiniFi, which you deploy at the edge to fetch the data, transfer it over to the server. We have multiple message queues, the most famous one, of course, being Kafka. And then as a database, as Xiangdong said, the first choice oftentimes is Cassandra for multiple reasons. But one reason is that the data is generated so fast that it's hard to find another system which is able to swallow it in time, because you're really throwing tons of messages on there, and it's something a regular RDBMS cannot handle. So we really have to look into these NoSQL databases. And analysis can be done, for example, with Apache Spark or based on Hadoop or whatever you like. And some issues we have with this stack is that really here are some numbers of data we produce, and in a simple example for the wind turbines, we get 500 million points per second, and this is really a challenge for every database, basically. And the other thing which hits us is the volume, because not everybody can or wants to sustain a cluster just for storing the data, and in some situations we want to make decisions faster at the edge, and then it's even harder to control all the data storage there. Because systems like Cassandra are not made to be storage efficient. They have other USPs. And then, yeah, we have some other things like sparse tables, because not every sensor reports at every timestamp. And we have to deal with things like out of order, which Cassandra just stores the way it is, but it would be better to store it in order probably. So this is basically one of the motivations we have. And the second one is that ideally, especially with NoSQL, you try to store the data in a way which makes it easier to query it later on. So things like the time dimension is something special when thinking about time series data, of course, because it's like a primary index and you usually filter on it and aggregate on it. And the second thing is aggregation is important. If you've ever worked with InfluxDB, for example, which is another famous time series database, they have this really, really lovely feature that you say, okay, give me data from this range, but only 1 point per minute, and just take the mean of the values in there. Because if, for example, I want to visualize something, I do not need thousands of points, but I only say, okay, I want 100 points in this range here and aggregate things. So this is something as from an API perspective, which is really, really crucial in working with time series data, because it helps you to keep your queries nice and easy, but yeah, make it way, way better accessible. And yeah, the second thing with current formats is that you really do all the stuff on your own. So the first thing is you swallow the data, then you transform it in some kind of ETL job which runs asynchronously, takes time, but also takes computational resources. So the main things we want is something to start large volumes with high throughput, ideally somewhere low cost from a hardware perspective, low latency for queries, fast and easy aggregation, and query capability for hybrid workloads. And if you monitor the current market of solutions for time series, there are quite some. Cassandra's the HBase is there, and then some systems based on Cassandra, like KairosDB, OpenTsDB, Timescale, which is a rather young project based on Postgres, and well, you can also do Postgres plain, and InfluxDB I just talked about, and none of them really fits for this topic. Many of them come from the monitoring area, where you want to monitor a cluster of computers, and when you push the workloads really, really hard, then they degrade either in performance or in storage efficiency, or in both. Later on, we have some numbers prepared to really show that from a user's perspective, you will hit issues there. So this basically is some kind of motivation why the world needs such a time series database. And now I hand over to Xiangdong again to tell you a bit more about how we tackle these problems to make them easy accessible with IoTDB.
Thanks, Julian. And now I will introduce some details about Apache IoTDB and some real use case about IoTDB. Okay, to meet above requirements, we built a time series database called IoTDB. IoTDB focuses on time series data management and has outstanding performance. For example, a single server with IoTDB can manage tens of milliseconds, tens of millions time series, and the trillions of data points and tens of terabytes data on one node, and also supports current big data analytics softwares. Overall, IoTDB has the following features. Firstly, it has high performance for data ingestion and provides high compression ratio for saving data and saving the disk I/O. Secondly, its latency remains low when querying on terabytes of data, and it supports time range query on with value filter and fast aggregation queries. Third, it supports many time series exclusive operations. For example, you can segment a time series into some subsequence. For example, I have a car or I have a truck, but I drive 1 hour and sleep 1 hour and drive 1 hour again. And if you want to calculate the average fuel cost, you cannot use the total time because you sleep several hours and you turn off your car. So you have to cut a time series into several subsequence, and then you calculate the each subsequence and do an average of the total result. And for example, we can support subsequence matching. For example, you have a long history of a time series, and you want to find a similar pattern. For example, like a curve or up and down curve and something others. And these are some operations only used for time series, and I think many databases, especially for relational database and key value store, does not support. And we also integrate it with current big data systems and some traditional softwares like Matlab, like Grafana, MapReduce, and Spark, and something others. Therefore, now IoTDB can cover the whole life cycle of time series, from collect data from the machine and then store the data and analyze data and visualize the data. This is the architecture of IoTDB. We provide 2 interfaces to users. The first level is the file level interface, as shown as a blue rectangle in the picture. Users can save time series data as TsFile, as a file format, as a file called TsFile. TsFile is similar with Parquet or RC files, and I will introduce the difference between them. And the TsFile, the difference is TsFile is optimized for the time series data. It plays the role of file layer of IoTDB. TsFile can be recognized directly by Spark and MapReduce, so that you can use these big data analysis softwares to analyze the data in TsFile. And the second one is the database layer interface. Users can use SQL to write data and query data from IoTDB, and IoTDB will organize the data as several TsFiles on disk locally, and now IoTDB can also write data directly to HDFS, so you needn't copy the data from your disk to HDFS and then use Spark or MapReduce or Hive to analyze it. And we provide a synchronized model among IoT instances. For example, it is quite useful for to collect data from many factories into one data warehouse. For example, if a company has several factories around the world or around Germany, you can deploy you can deploy the IoTDB instance on each factory, and on each factory it manages the data in this factory, and then you can use synchronized model to synchronize the TsFiles from this IoTDB instance to your data center, the IoTDB instance in your data center, and then you can get a data warehouse. IoTDB's schema is quite different with other systems. There are 3 concepts: device, measurement, and time series. A device is a machine instance. For example, my car, your car, my iPhone, your iPhone, and so on. And using the vehicle management as an example, we can use the country, the state, and the plate number to represent a vehicle. And a measurement or in some applications is called a metric or a variable. It's a variable that users are interested in. For example, the vehicle speed, your phone's remained power, or something others. And a device can have many measurements. In our applications, when the turbine can have more than 500 measurements, and a metro train has more than 3,000 measurements, and I will show you the real applications later. Given a device and a measurement, we call its data from a time series. Therefore, the device and the measurement name form the time series ID. And we use a path to that concatenated by dot to represent it. For example, root.catalog.active.us.ca. And to help organizing these devices, we propose a new concept called the storage group. If some devices have the similar measurements, we can assign these devices into a storage group. But remember that we do not require that all the devices in one storage group has the same measurements. Actually, we can map our schema to other systems. For example, suppose we have 3 time series like the top left. And the bold black strings, for example, root.catalog.active is the storage group name. And the black and red color strings are device names. It's plate number. And the blue strings, the field remain, the speed, are 2 measurements. If we treat it as a relational table, it looks like that. And we can consider the storage group name as the table name. And the words in the device names form the country and the state and the device name columns, and to represent the devices. And the measurements, for example, field remain and speed are value columns, and there's another column called the timestamp. If we treat this table as a Cassandra schema, you can consider the country, the state, the device name as a partition key, and the timestamp as the clustering key, and the field remain and speed as the value columns. And if we treat it as some other time series database like InfraDB, OpenTsDB, or CurseDB, then the first 3 columns are tags in these systems, and the last 2 columns are fields in these systems. One more thing, when we treat the schema as a relational table like this, we can find there are 2 cells always be null, because this vehicle maybe has no field remain measurement. That's why Julian said that if we use relational database, we may get a sparse table. And IoTDB now provides a SQL interface to simplify how to use IoTDB. And we can create a time series, insert data, delete data, and support many queries. For example, in this picture, we can see a value filter, and we can transform the time series from time domain to the frequency domain. But this function is not implemented now. And aggregation operations, and this is a downsampling applications for you can downsampling data by each hour just get its count value or max value or some others. And now IoTDB supports this basic data type, and we may support some complex data type, for example, GPS or array, to support more applications. And this is the printed result by our command line. And now I will introduce some detail about how IoTDB implements. The first one is TsFile. We call TsFile as a zip file bound for time series data. TsFile is a column file, and it is one of the main technology in IoTDB. We use column store to reduce the disk I/O and improve the compression ratio. And we propose some encoding methods to let the compression better. And actually, TsFile is quite similar with Parquet, but it has better performance for time series data, just for time series data. And let's see the difference. TsFile is inspired from Parquet. And the concept in TsFile and Parquet are similar, but TsFile has its definition. For example, the trunk group in TsFile is similar with the row group in Parquet, but in TsFile, a trunk group only stores the data that belongs to one device. And the trunk structure is similar with the column in Parquet, and the trunk only stores the data that belongs to one device and one measurement. And the concept of the page is the same with Parquet. And there are some detailed differences. For example, the first thing is that in each page, we do not only store the measurements values, but also their timestamps. It is because that we have said the timestamp column is always be read. So in this way, when we read in one time source, we do not need to stick on disk and do not need to use the repeat and duplication fields like in Parquet to align the two columns. And by reducing the disk stick I/O, this performance can be improved. Secondly, because we know that the data is time series data, so the page and the trunk header can have many useful information such as the minima and the maxima values in the page or in the trunk, and the maxima and the minima timestamps in the trunk. Using this info, we can accelerate the query filter. And third, the file metadata is also changed. Because one file may have many time series, maybe one file has tens of thousand data and time series, and we may be unable to load all the file metadata into memory. Therefore, we use the two levels metadata now. And we do not use Thrift protocol to serialize data in TsFile. It is because that IoTDB is an OLTP system, and we need to repair the data file if the process is shutting down abnormally. And so we need to know what is the mean of each byte in the file. And if there's a broken file, we can fix it and append the new data at the tail of the file. And however, it is hard to do that using Parquet because in Parquet they use Thrift to serialize the file metadata. And TsFile implements a list of encoding method technology for different data types. We adopt dirt of data encoding called TS2diff that stores time series data and the value data. By calculating the dirt of data, the diff value is very small, and then we can use few bits to store them. But the compression will fall if there are many outlier points or the data sampling is irregular. But this scenario is very common in industrial applications. So we further design an adaptive version of TS2diff encoding, which can encode the time series data with outliers or missing data points efficiently. The technologies, we can cut a page into several pages to avoid some missing the effect of some missing points, and we can save the outlier points separately to get a high compression ratio. And for integers with screenshot repeated values, for example 5555, 44444, we adopt ILE, namely run length encoding, and it encodes the repeated sequence by just storing one value and the count. And bit packing is for storing the integer data by using compact bits rather than using 4 bytes. And for floating data, we implement Gorilla, a lossless encoding algorithm provided by Facebook. And after encoding the sequence into binary array, and we further compress it once again using some well-known compression algorithm like Snappy and others. This is a detail about our adaptive encoding method. Actually, we just using this algorithm, we can check which point is better to split a page into several pages, and we may fill some missing points to get a better compression ratio. And the left is a part of SQL that IoTDB supports, and we propose some indexes to accelerate the queries. For example, we propose the PISA index, PSA index. PISA index can let IoTDB get the aggregation result in few milliseconds on billions of data points. Actually, it is pre-calculate data first and organize the pre-calculation result in a forest, not a tree. And these are two indexes for supporting finding the subsequence or finding the pattern among the whole time series dataset. And the left is for streaming data, and the right is for historical data. These are two papers, and but we are doing to implement them into IoTDB. And IoTDB can be deployed for a variety of purposes. For example, sometimes we can just use TsFile to store data, and sometimes we can use IoTDB to support complex queries, because TsFile only support write data and some simple query. And we can deploy IoTDB or TsFile on embedded devices like Raspberry Pi, on a computer in a factory, and deploy an IoTDB cluster on a data center. And let's see how IoTDB works for time series data management. Because IoTDB provide SQL, and we also provide JDBC, and you can use JDBC to write data or query data. Before you write data, you need to define the schema. For example, here we call them as story group and time series. You can define the time. We let users define time series because users know what data type the data is and which encoding method is better. Users maybe know that, because if you know that your data looks like this, you can use because it's a sine or cos function. So maybe you can use some good encoding methods. Or you can implement yourself encoding methods. But if you find that if you know your data looks like this, then you can use your IRE encoding method or bit packing or some others. And then you can insert data using insert clouds. And now, actually, in our latest version, we support to define the declaim the time series schema automatically, and that means users do not need to create time series, create time series sentence, but maybe we cannot get the better encoding method. But maybe later we can introduce some AI technology to get a better encoding method. And if you embrace the performance, we can use raw data, raw level API to skip parsing a SQL. Currently, we use Untitled 3 to parse the SQL, but we found that the time cost of parsing a SQL is very heavy. So we provide a raw level API to skip parsing a SQL, and it is far efficient. And in our latest version, you can use that API. And if you're using JDBC, you can use result set to query data and scan the result. And we have integrated IoTDB into Grafana by using the Grafana's simple JSON plugin. We provide a RESTful server to convert IoTDB result to JSON format. So you can use the simple JSON plugin of Grafana to view the data in IoTDB. And you can in Matlab, for example, there are many in many factories, the data scientists do not know how to use big data systems. They just know how to use Matlab or how to use R language and something others. Then you can use JDBC in Matlab. You can use JDBC to query data from IoTDB, and then you can use Matlab to do some calculations. For example, like FFT. And using Spark SQL, you can query data and analyze data from a TsFile, or you can also query data from IoTDB instance. And I will show 2 demos here. And the first demo is how to using IoTDB to write data and show data with Grafana, and using Spark SQL to analyze data. And the source code is here. And in the second demo, I will show how to write data by using IoTDB to write data on HDFS directly, and using Hive to analyze the data. Because I didn't install Hive in my laptop, so this is a video. And let's see the first demo. In this demo, oh, sorry. Actually, I want to integrate PLC4X with IoTDB to show the demo, but I have no PLC here, and there are something others. So I write a data generator class to collect the data from my laptop. It can collect the CPU, the memory, and the total CPU and the process CPU. The interval is 1 second. And actually, the source code contains you can collect the data and send the data into Kafka or MQ, and then consume data from MQ and save it into IoTDB. You can send the data into a MQTT server and consume data from MQTT server and write it into IoTDB. You can also write data directly into IoTDB, and you can also write data. You do not need to start IoTDB instance. You just write data into TsFile. Okay, let's see the first one. You can write data directly into TsFile. I remove this one. And when you write data directly into TsFile, it's very easily you can see. Okay, you can create a TsFile writer, and then for each measurement, you need to register it by to tell TsFile what data type it is and which encoding algorithm it uses. And when you write data, you just tell TsFile the device name and the measurement name and the time and the value, and you can write data by this. And finally, you just close the data, close the TsFile. So let's see. Okay, we have at least 10 seconds. And you can get a TsFile here. And this file is very small, maybe several thousand bytes. And actually, we provide a tool to print the TsFile, because this is a tool provided by IoTDB. You can print the sketch of TsFile. It's help to know more about TsFile. It print which byte means on TsFile. You can find okay, there are many there are many trunk groups, and for example, a trunk group like a time series called the name like this, and its start time is here, and the end time is this. So this is our what I mentioned before, our information about for faster query, and we can use firstly let's use Spark to read the TsFile for some of analysis. For example, we just read the data from the TsFile and run a Spark SQL. Okay. There are two commands. The first one is show the data, and the second one is show the count value. Okay, this is a count value, and this is data in relational table, and you can see it is a quite sparse table. And we can also use IoTDB to run. I run IoTDB firstly, and because I ran this demo several 1 year or 1 hour ago, so now there's data. There are so many time series now, and we can select maybe test from CPU from root. You can see there are two devices which have the measurement called test CPU. The first one is system CPU, and the second one is the process CPU, because just now I run a process. And we can use like this to get both the two devices info, the CPU info. Oops. Root.test CPU. Oh, sorry. It should use. If you do not want to write app, you have to write like this, and you can get there are two devices having the CPU result. And using this is now we have an IoTDB instance, and we can run Spark to directly analyze data from IoTDB instance. You do not need to define which TsFile you are looking, and but just by this program, and it's quite similar with the previous program, but because I have no time, so I will skip this. And the second demo is how to write data on HDFS and use Hive to analyze data. Okay, the first one is a demo for. Firstly, in our latest version, you can define which where you store data. Local means your local disk, and HDFS means you save data on HDFS. And you need to define claim where your HDFS is. And then if you start IoTDB, you can say you can find that your data will be stored on HDFS directly. So this architecture is quite similar with HBase, right? This is create time series and insert some data, and then we call flash to we call command called flash to let IoTDB flash data. And you can find on HDFS, you can find the data. And because the data is on HDFS now, and we can using Hive to analyze the data. Oops, sorry. When you start Hive, and you need to add a jar file to let Hive know how to understand, how to parse the TsFile. And then you just create an external table like this, and claim where it is on the HDFS. And then you can describe table and select and run some select commands. For example, like this. Okay. Wait one moment. This is okay. And if you want to know more about this demo, you can get the source code from here. And currently, we just provide Java API, but because we the RPC level RPC model is implemented by Swift, so maybe you can get other language APIs. And we have integrated IoTDB with Kafka, with RocketMQ, with MQ, and we want to implement it with CalSet and PL4X. Integrate it with CalSet, we can support standard SQL language. And there are some use cases. For the first thing, we use IoTDB to replace MySQL to manage some meteorological stations in China. There are about 150 meteorological stations, and each 5 minutes, it reports some data to the data center. And the second thing is we use IoTDB to replace the SQL Server in Tianyuan company. It's a Chinese company to help managing the devices built by Komatsu in Japan. And in these applications, we manage about 200,000 devices, and each device has generated up to 5,400 metrics. So they even though they just collect data per minute, but because there are so many devices, the data point can reach up to 1.5 trillion points per day. And the next one is we use IoTDB to replace CaresDB in Shanghai Metro management. In this application, IoTDB manages about 300 railway trains, but now it's about 500 railway trains, and each train collects 3,200 metrics every 200 milliseconds. So there are about 400 billion data points per day. And before we use IoTDB, Shanghai Metro used CaresDB and Cassandra backend to collect just 144 trains, and the collect frequency can just reach up to 500 milliseconds. But now we just use one IoTDB instance to collect more data than it. And I will show you the real application of the Shanghai Metro data management. Because this application is deployed in Shanghai, so the network is not very good. So in Shanghai Metro, there are about 15 or 17 routines in Shanghai, and we can see the status of some trains. For example, we can see this is the ID of these trains in 17 routine or 17 line. and this is these are the metrics of the train. For example, whether the door is open or whether the door is closed, or the and the maybe the how many persons in the train, and something others. And we can collect data. We can query data using this page. And for example, now there are totally about LAN 1, LAN 2, LAN 3 until LAN 17, but there's no 14 and 15. So there are totally 15 LANs in Shanghai, and each LAN there are about 26 trains. So there are about 400 or 500 trains totally in Shanghai Metro. And for each, for example, let's see. I don't know. I just tried this train. And for each train, let's see how many metrics or how many measurements there are. You can see there are 10 mirrors in this train, and there are 319 pages. So there are totally 3,190 measurements in each train. And we can see we can query the data. Okay, this is Chinese word. And we can scan 1 day's data, because this system used the CarsDB preverse. So the developer gave tips to say that if you want to scan 1 day's data, it's because there are so many data, so the time cost may be 30 minutes, 30 seconds or later, or longer. So, but now if you use IoTDB, it's very fast to get the data. Yeah, and because the times and Julian, do you want to introduce this one? Okay. So in the future work, we want to integrate IoTDB with maybe with Calsite to make it easy to use. Integrate it with Hive to support using Hive to write data directly, and deploy our cluster version and support more advanced functions. So that's all. Thank you. And any questions? Yeah.
First of all, very nice talk, very interesting. The first question I actually have multiple questions. First question I have is, what is the resolution of the timestamp? Is it fixed?
Resolution?
The resolution of the timestamp. So
yeah.
what is the minimum unit of time I can put into the database?
Yeah, actually, we just store timestamp as a long type, and we can let user define what's the mean of the long time. Yeah. You can define it as a nano time. You can define it as a millisecond time or some others.
Okay. Yeah. And the second question that arose in my mind as you were starting IoTDB, have you experienced any difference in the performance which file system is used? For example, if you're spinning it up on Windows, is it significantly worse than on Linux, for example?
With InfraDB?
With the IoTDB performance.
Okay. Actually, I have the slides. Let's see it quickly. For example, the compression. You can see we compare IoTDB with InfraDB with TimescaleDB and CarsDB, and TsFile is another Chinese time series database. You can see we store 100 gigabytes data, and IoTDB only use 8 gigabytes. And but for the
my question was more or less if the underlying operating system or the underlying file system to which you are writing your files, if this has changed, for example, you're using NTFS on Windows and you're using X3 or something like that on Linux.
Okay, we write data by using Java API. So we write data directly on the disk.
Yeah. But you're still relying on the OS layer.
Yeah, the file is, as shown previously, the database is based on these TS files, which are basically a bit like in HDFS. There's the minimum packages which are like 200 megabytes or something. So we have not the issue with Git or something that you have too many small files. So therefore, it basically doesn't matter which file system to use. There's no really in-depth examination we have done, but it doesn't matter that much as we just do bulk writes in big binary files.
Yeah. And then.
If you write data directly on HDFS and you write data very fast, insert data very fast, there's maybe a pause, because you write data on HDFS too fast.
Yeah. And then my last question: at the moment, you're supporting JDBC as an adapter. Are there any plans to support other language or other adapter possibilities, for example, to extract data directly from Python or stuff like that?
Yeah, we can use Swift to compile the API of Python and C++, but we do not support ODBC or some others. Okay. So if you read the source code of, actually we have 2 PRs pull requests now, and one is for support Python and another is for support C++.
Another comment from my side, probably we have some Arrow people around here, because I think Arrow would also be a pretty nice fit, as we have rather large data sets and it's a nice way to transport it basically from Java to Python or whatever. So probably if we get on this conference in contact with some Arrow guys, it would be awesome to discuss with them how to basically make the data more interoperable.
Python to write data and query data, but it's not merged in our master branch.
Okay, thank you.
Do you support any retention policy on your data?
Yeah, now we are supporting that. You can see this one, and support storage group level data TTL. Yeah.
Okay, thanks.
And so maybe the questions overlap, but I was going to ask about aggregation of past data, such as I think you have in OpenTSDB, the capacity for the system to aggregate, so you don't keep too much data in the system. Do you have these or?
So now we do the there's no limitation about the aggregation. You can define. You can say I want to do a downsampling or aggregation for 1 year's data, or for 10 years data, or for just 1 day's data. But the performance may be differ, may vary because how many data we need to read from the disk.
Okay, but so you don't downsample automatically. It's at query time. I have all the data accessible all the time.
Currently, we do not downsample data automatically. But now we are implementing the PISA index into IoTDB. After that, the downsampling data will be stored automatically before you query data. But now, we think our aggregation speed is very fast, even though we do not calculate. We have some info on each file.
Another point which probably comes with the calcite integration. When we integrate calcite, then we have a powerful query planner and can use material as views as kind of indexes, and then it would, from our perspective, be more elegant to provide indexes for aggregations you search oftentimes for or you configure, because for industrial data, usually you need the raw data at any point in time, but probably you want to have some regular intervals faster. So the idea is, if we have the calcite integration, then we could add something like this, that you say, okay, I want an index for 10-minute samples, for 1-day samples, and then you basically get both. All the data, but with the speed you want, basically.
And another question, if I may, do you have, so you made demos around trains and so on, so you have many moving things. Did you integrate some geographic or coordinates in the model, or do you have any support for that? Or
So-
is it not?
So
unusual?
currently not. We haven't support geographic data. That's why I say maybe later we can support GPS data or something others, support trajectory data or something others.
Thank you.
Okay, thank you everyone.